This is our last webinar for the spring series. At the first, I'm going to briefly introduce SZ4D, SZ4Grads, and then I will give a brief introduction of Walid, and finally, it will be Walid's turn to introduce his work. And whenever you have question, you're always welcome to type in the question part at the bottom. So, SZ4D stands for subduction zone in 4 dimensions. We are here to understand the limits and possibilities of predicting subduction zone geohazards. SZ4Grads is under the umbrella of SZ4D. It's a collaborative, interdisciplinary, and intercultural network of graduate students and recent graduate students studying in subduction zone processes. During this webinar, we've got live translate closed captions. You can find the button at the bottom of your screen. We also have recordings. We will upload them to YouTube to catch up later. At the end of the webinar, please fill out the survey. I'm putting it into the chat so that we can make sure we're reaching everyone. The webinar would be around 45 to 50 minutes, 45 to 50 minutes. And we also have another advertisement during SSA. SZ4D is hosting an SIG. I'm posting that to the chat again. Oh, sorry. I think you're able to see it now. This is called special interest groups. We have the SIG meeting throughout the SSA meeting from May the 1st to May the 3rd. Basically, from all of the sessions, you can know what SZ4D is about, and also we can help you better engage in it and find your position here. So yeah, for today's webinar, we are honored to invite Walid to be here to give us a shocking, a very good presentation. So Walid received his master's degree in geophysics from University of Nice in France. He traveled a lot. He got his PhD degree in seismology from University of Leicester in the United Kingdom, and he did his postdoc studies in Macquarie University in Australia, and now he is currently working as a research scientist in Washington University in St. Louis. So this is like a pretty good CV, and we're really looking forward to your talk. So the floor is yours.
Well, thanks. So I will just share my screen. Can you see my screen? Yes, okay. So today first, thanks to give me the opportunity to discuss of one of my projects I'm doing here at Washington University in St. Louis in the US.
Sorry, Willie, we can't see your screen.
This is why I ask. Okay, this here. You see?
Good. Thank you.
So today I will discuss one of the projects, and the close-up one, very close to SZ4D, is about the Patagonia subduction zone. And I will discuss a little bit for a few slides about the technique I try to apply, why it's new, and why it's interesting to use it. So this work is with my boss here at St. Louis, is Doug Wines, and collaboration with Valérie Maupin from Oslo and Shuwei Wang in Taiwan. Basically, the person developed this approach. So I will just go for 3 slides, I would say, about the technique. I will try my best to explain in the best way, even if it's obvious for most of you. So most of the time we use grid theory to try to estimate body wave travel time, so the first arrival from P or S. And this is based off high frequency information using a very basic straight line between source and the receiver. And ray theory ignores generally scattering and diffraction effect. So it's a very strong assumption. And we assume that everything is along this ray path. So you can see on the right here, cursor in red. Yeah, or maybe not. Anyway. So you can see that the ray path just crossed the anomaly for a given site. And this approach is useful because it helps us, for example, to determine the radius of the Earth core in 1910, the discovery of the teeny inner core in 1936, or also build this spherical Earth model that could accurately predict seismic travel time. So this approach is very powerful and gives us a lot of information. However, there is some limitation using this ray theory, especially when we think about the size of the object we want to sample. And we are limited by what we call the Fresnel zone, which is a function of the distance versus the wavelength of the seismic wave. So far we are, and low the resolution we get using this approach. So to address this problem, basically when people try to use this cross-correlation method to estimate the travel time residual, so the difference between what a given model like AK135 predict as arrival time of the P or S, and what we pick as the P or arrival time, so the predicted minus what we observe or run around. So they realized that if we want to capture the 3D information, we need to don't use like a ray path, only a very infinite information, but what we call this final frequency wave. And basically, if we go to the literature, back to some textbook, we basically use what we call this first order Born approximation. And then we can consider this single scattering approximation, where we can put perturbated wave field due to a small perturbation. And then between the source and the receiver, we don't have any more like a small line, like a teeny line, but like what the banana shape, where everything with the size of the shape will give us the size of the anomaly we can capture there. So here is an example from this early paper in 2000 by Dallon, where we can see this banana shape is a function of period, and also depending of what we want to look at. So if we look at very small period, for example, at 2 seconds here, the banana shape are narrow compared if we look at 20 seconds. So the advantage of this approach to final frequency travel time tomography is we can explore larger range of phase information to constrain the structure. And also when we filter that for different frequency, we can also change, or say the width of this Fresnel zone. So here is an example from a paper by Juan in early 2000, looking at the direct P wave and direct S wave. And you can see this Fresnel zone is frequency dependent. So if we use, for example, for P wave, frequency band between 0.5 and 2 Hertz, we can sample anomaly between 4 and 50 kilometers. And if we want sample, I would say, larger anomaly, we need to go something like 0.3 and 0.1 Hertz. And these are also an effect about the peaking of the PNS. For example, here is an example of P wave for long period and short period for different frequency band. And you can see there is a difference between, for a given station. So number here are the station. There's a difference between short period and a long period period time using this frequency analysis. So as explained, we can use different phases now to try to explore the anomaly in the Earth using this approach. So we can use like GIP wave like on the top, and we can combine everything like on the bottom one where we have all phases from the mantle to the core. But when we use that, it looks like we have a very good coverage, but we have always to be careful about what we include in the data set we want to explore, because there will be some bias due to some conversion between these different phases. So in my work, I mainly use just the P-wave. And P-wave give us enough information to sample the mantle. So what I discussed before is not new. So finite frequency tomography is used for many years now, from body wave or from surface wave. So what is really new here in the case here, and my work with my colleague in Europe, in Oslo, is we try to think about what is the effect of using different, what we call asynchronous seismic network. So if we have temporary network from different period of time, what will be the effect on the seismic structure we get there? Especially when we think that for body wave travel time is a relative travel time. So we can be, so we have a given event, we have a mean value which will affect, I would say, your final model. So here was an example in Scandinavia, in Norway, where we have different configuration of seismic network. So on the right is the real network in Norway. So the color is give you some different network. The red one is a temporary network, all one, what we call the Magnus network. And on the blue one, it was a new network, was a scan array. So two different network in time, and the color and the dot is give you the number of events recorded for a given station in a logarithmic scale. And you can see on the right a map of the earthquake used there. So the red and blue are for different events there. And when she called distributed setup and decision setup, it just rearrange artificially network. And what we want to see if we have like a disjoint setup, so completely different seismic array without any connection, can we get a real I would say model at the end, or there will be some artifact due to the configuration of the geometry. So she tried to test that. And main assumption, as explained here on our paper, is travel time at station in a regional network are affected in a similar way by error in source location and origin time, as well by large-scale heterogeneity in the lower mantle, and that by only accounting for the travel time difference between station, these effects are considered or removed, and the residual can be inverted in terms of structure beneath the network only. So this is a strong assumption when we work about travel time for regional network for different networks. So why is it important to think about that? Because we can have a large-scale bias if you try to combine network from different period of time. And in the community of, I would say, body wave travel time tomography, I would say colleague doesn't really care about if this network was running at the same time, if we have the same number of stations at the same time. So putting all together gives you a model, but there could be some bias. Not every time, there could be a small one or very large bias on the final model because they try to combine network from different period of time. So what is new here is we try to use that situation because in our case, I will explain later, we have this situation where we have asynchronous seismic network. So in the test she did in Scandinavia with these two different configurations, she put as a synthetic test an anomaly between 100 kilometers and 200 kilometers, as you can see on the left. So given location, you can see on the map on the 200 kilometers. And she inverts as the normal travel time tomography. As you can see, for a given depth, for example, at 200 kilometers, we are able to recover very well, even if we have what we call a very well distributed setup, which is the figure on the left, or if we have network completely separated. So there is no bias. And this is basically because we are able to resolve the contrast between east and west thanks to the overlap of the kernel at a given depth, which link the model to west and the east. So the inversion tend to adapt the difference in average between east and west and incorporate model parameter in region of overlap that fit in both setup. This is what is new in this approach, is we try to use this relative kernel and try to use different network with this approach and try to remove the potential bias we can get if we don't use this approach. So it was the very fast, I don't know if it was clear, but very fast part of the technical part, I will say, of this the method. And then I will go to the study area where I will apply this technique. So if you go south to South America, we are in Patagonia. And as you can see on this figure on the left from a paper, I forgot to put reference. So you can see there is a very strong difference between the northern part of Patagonia and the southern part. So there are more seismicity in the north and almost nothing in the south. What is interesting about Patagonia also is also a region where we can find ice sheet, one of the last ice field. So this is a figure, is a model, the Batiste model, where there are a construction of the size of the ice field in the last 45,000 years. And you can see now the ice field is very small and located mainly in the very south of the continent. So we don't have that much seismicity, and the ice sheet is also very small. So if we look at a little bit about volcanism, we can see that we have arc volcanism, the black triangle, stop at 46 degrees south. And we have a gap in the arc region, and we come back with some arc volcanism around 49 kilometers. And if you look at the back region, we have, I would say, a lot of back arc volcanism. So what's, I would say, going on here? Well, if we look at some prior reconstruction, this is a paper from Borkelston and Borkelston 2019. So we have the subduction of the Chilean spreading ridge in the south of the continent beneath South America. So when the spreading ridge was subdued beneath the continent, they generate a window, asymmetric window is what we call the slab window. So the slab window was 12 million years ago in the south of the continent. And with time, you can see the extension of the present day location of the edge of the plate. The Nazca plate now is around 46 degrees south. And this was mapped not from geophysics, but from geochemistry. So on this figure, you have two different colored dots here. So the black dot shows some basaltic volcanism, magmatism, and the blue dot show you some alactitic volcanism. So the differences here is just show you the effect of the window on the melt of the slab. So the blue part means that we have some melt of the slab, some signature of the melt of the slab, and the red dot means we don't have nothing there. So it's how they were able to capture this slab window from magmatism there. So if we go a little bit about seismology here, so here is some recent seismic model in South America. On the right is the seismic network we can have in South America before 2022, I would say. So you can see there is a little gap in the seismic network, and I will discuss that later. And on the left and middle is some VS model from the group in Dublin. And we can see for different depth, for 485 and 110, we have a very clear signal around the triple junction, I would say, where we have the Nazca plate and the window at 110. And they also capture some fast VS anomaly, deeper depth, they interpret like a stagnant slab there. So because we have a thermal anomaly, they also generate some uplift. So here is some GPS vertical motion associated with some GPS measurement from Bedoza et al. 2011. So you can see from south to this, I would say, triple junction, we don't have that much detail. This is basically because I didn't discuss that, but this is another model from adjoint tomography, where we have more, I would say, more station and more detail. But the main point here is south to the triple junction, we don't have much station. So here is the station we want to use here to improve the resolution and the detail of the mantle structure in the slab window. So we have a network, a whole network from 2005 and 2006, very dense network around the triple junction. And what is very new here is we deploy between 2018 and 2021 temporary net station in southern Patagonia, which give us more information and detail about the crust and the structure in this region. So we had more coverage to get more detail compared this previous and recent model. In the figure on the right, it doesn't show any result from south of 40 degrees south, basically because there was no station there. So with that new data set, we can improve this the detail of the structure there. So what one of our postdocs did at Denmark when she was at St. Louis, she did some receiver function and ambient and earthquake analysis to produce a new VS structure of the region. So here are three depth slides at 50, 100, and 150 kilometers using this network I showed you before. And one of the three main points here is the mantle velocity low from the infrared slab window. So where we think there is a slab window, we have very clear signal, less than 4.1 kilometer at kilometer, as you can see here on the left. And about 8% slower than, I would say, the global average for a given model, the ESTW105. So now to 51 degrees, so I can show here again on the map, the western edge of the anomaly at 100 kilometers align with the estimated extent of the subduction of the slab. So we're able to extend the anomaly where previous study was not able to get that much detail about the certain extension of the slab window here. So we get that as a new output. And we also be able to show that there was presence of a contralithosphere block more in the south, close to the Tierra Fuego, which is the blue part in this figure. So this was one of the new outputs. And the other new output from this study is from Denmark, 2022, is we get a new sediment thickness map and a more map. So we got a new crystal model, which are very important, especially when you do some body wave tomography, because you have to do some crystal correction and have to remove any effect associated with the crystal thickness and sediment thickness. So the new model we will provide for the slab window in terms of body wave inversion will include this information. So in addition, when I start my work here in St. Louis, I did very quickly some shear wave splitting analysis. So here was a paper we published also in 2022. What we show here, what we observe is, we observe very strong splitting up to 2.5 seconds with east-west fast direction, just south of the triple junction, here at the edge of the subduction slab. So basically where we have this very low VS anomaly. The region of flow corresponding to the volcanic gap causes depleted mantle composition and absence of slab-derived water. So is why we think we don't have any volcanism in the arc region in this region. And the certain most of Patagonia of the south of the channel splitting fast direction trend like northeast, southwest, which is consistent with large-scale asthenospheric flow. So if we just back quickly here, we can see I have different depth at 60, 100, 120, and 200 kilometers. And on the 200 kilometers, I compare by splitting result with a global model. And we can see that this northeast southwest direction correlate very well with what global model give us. So it's why we have this very simple cartoon we put on our paper in 2022. So I would say we got a very nice first results. However, the surface wave tomography is limited in terms of depth. So basically the result from Mark et al. Didn't give us more detail deeper than 140. So it's why we want to use body wave to extend our picture of the slab and the slab window here. So here, what I did, what I'm doing, what is the goal to complete this work is to use all seismic stations we have in this region. So we extend a little bit north of what Anamark did. So here we have two different data sets. So we have this white square, which corresponds to temporary network between 2004 and 2006, so late 2004 and mid 2006. So it's very focused in the middle of the region. And we add our temporary network, which is also located on very specific region between 2018 and 2021. And we include the permanent station from the Chilean network, which are the red triangle, and also the permanent station, the GT network. So altogether, we try to get maximum information as possible, and by using this relative kernel, as I explained with Valérie Maupin, we try to remove any bias associated with this large extension of the study area, which is about, it's a very large area for the rational scale. So basically what we do here is for given events, we try to find the P wave. So here is just an example of what we have before any final processing. And the goal is to try to estimate what is the difference between what a model, AK135, which is the difference between the AK135 and what the P wave arrival at a given session gives us. And then using different techniques, so the classical iterative cross correlation, we align the waveform, which is give us an estimation of the residual travel time for a given event at a given station. So what we built is a P travel time residual. So for example, here is an example for a given event. On the left, you have the relative travel time residual, and on the right is the time difference. So you can see it's very, I would say, there are a clear pattern between the north on the triple junction in the blue, and I would say the south of the triple junction more red. So we do that for all stations or events we have for P. For here is just a screenshot example for different period of time. On the bottom is the P relative arrival time, and on the bottom are the S relative arrival time. So when you have a cluster very narrow around 45, 48, it just means we are looking at the period of 2005 and 2006. And when you have something more spread, like in the middle here, it's like we are looking the period 2016, 2023. So it's 2 periods of time, and the goal is to try to combine these two networks and fill the gap to get more detail between what is going on between the Nazca plate and the slab window. So when we have this P and S residual travel time, what I didn't explain, I forgot to explain that before. So we use multi-frequency analysis, as I showed you before about the kernel. So for a given kernel, the width of the kernel will depend on the frequency band we use. So we use 2 frequency bands for the P and 1 frequency band for S to be able to get information about high frequency and low frequency. And then we have this data set, and we use this multi-scale final frequency tomography with this configuration for the grid parameterization on the right. And we can see on the middle and right is just an example of the the potential of using this multi-scale in terms of data fit versus the model variance. So you improve this, reduce the misfit, you improve the quality of the model using this multi-scale, compare using a different kind of inversion approach. So here I will just show you just some very preliminary results. There will be some update as I wrote here on the slide. So this is what we can get using just the period of 2016-2023 from the P residual. So we can see some different depth slide. So I also put here very quickly the extension of slab window in red. And we can see we are able to recover some anomaly associated with the asymmetric window. So you can also see there is some weird, I would say, low anomaly very north, which is for the moment associated with a problem with the station. So there will be some control here to understand why we have this anomaly, if it's due to the station by himself or is due to the crustal correction. Because the problem, if you have a wrong crustal correction, we get some problem in terms of estimation of the travel time. So it could be also a problem with the crustal correction. But however, we get our first VP model here using two different frequency bands. I will say there will be a new model soon, and we hope to finalize it very soon. So we also run for this very small array, the 2005, to see if we get similar patterns of blue and red, the transition between the Nazca plate and the slab window. And we are, I will say, happy in first order about what we get. So the goal now is to improve that a little bit and use this relative kernel to merge these two models, I would say, because these are two inversions for two different data sets. So we do similar work for S. I don't have any figure to show you today. I would expect to have this week, but we have some delay in terms of checking the quality of the data. So I don't have any model to show you today, but there will be soon some result for that. I wanted just also to show some previous results from body wave tomography in this region, because we are not the first group to try to do that. So the early work was by Ray Russo in 2010, using his network, the 2005 network, and he was able to capture for the first time the difference between the Nazca plate and the slab window. But because he didn't have any station very south, he was not able to capture the extension of this slab window. These are two slides at 100 kilometers and 100 kilometers. Then on the right, it was a paper recently published, but using a old network, also in the same region, because in this specific region, there was two seismic networks for the same period of time, but a little shift in the west. And also produce some anomaly, P anomaly in this region. But here they are using ray tracing, no, sorry, ray tracing, ray theory in neutral frequency. So in our case, we'll try to improve that figure in this specific region, if we can. And in terms of final frequency model, so what people also recently did, so this is a paper is on the review by a group in collaboration work by the Japanese and the Chilean colleague. So they tried to produce, I would say, a continental scale final frequency and rate travel time tomography in South America. So they, I would say, published before us, but it's not a problem because it's not, I would say, the same technique for different reasons, but they are able, using this final frequency, able to capture again clearly the anomaly we are talking about now for the last 10 minutes and more around the triple junction. Very low anomaly here, and a little bit some information about the Nazca plate, more slow perturbation. And you can see on the map on the right is the seismic network they use. So they don't really use much the network from 2010 in the slab window here. So the goal is to improve the transition between the Nazca plate using this 2016.93 network and the 0.5 station. And we have a bit more station also in the south to try to get a better full picture, high resolution PNS model here. So when we will finish, and I hope in I would say the next 2 or 3 months, the goal is from this seismic model, what we can learn from temperature, property of the mantle, and about viscosity, which is one of the questions the project wants to address is what will be the response of the mantle due to the ice mass loss of the Patagonia ice field. So there is different ideas try to deal with that. So here I just put some potential, I would say, approach we can use in our case to try to constrain the temperature and the viscosity property there. Even if Mark 2022 proposed a viscosity model using our PS model. In our case, we have some P model and S model, so there will be different way to address this question. And I would say as a final work, future work, and final part to wrap up this project is to try to combine information we learn from the surface wave, I would say high resolution for the upper part of the mantle and the body wave, so able to connect both models, so the model from Mark 2022 and my model, the body wave, to have a final 3D model of the region. And from that, try to get more inside the geology of the mantle here. So probably a collaboration with colleagues in US and Europe, and also try for final part when everything is published and wrapped up, if we are able to try to couple what we have at the surface, so landscape evolution associated with the ice field and the effect of the solid earth dynamics, so the slab window migration from south to north. That's it. Thanks.
Thank you so much, Walid. Let's see whether there are any questions posted here. Seems that it went very smooth. So people are like, I'll understand it. It's like, you made it easy to understand.
I try, but it's very, very, very technical because, for example, the first 3 slides try to explain the difference between which is standard ray theory tomography, what the final frequency can provide as more detailed, I would say, information, which is not completely new if you look at body wave and surface wave. Even if for surface wave there is some new development for final frequency using ambient noise, I don't think there is any final frequency using attenuation yet, if I remember well. So it's probably more challenging to do that. But then, yeah, go ahead.
Go for it.
But yes, in our case, we try to extract much information we can from the waveform we have. When you think about using some temporary network, so very short period of time deployment, we are the very south of the continent, so we don't have a very good, I would say, the best back-azimuth coverage from earthquake. The best event you get from subduction zone. So when you are in the subduction zone, most of the events from Patagonia are from Central America or from Tonga. We lost a little bit of information from the east part, which is from Africa, Europe, and we're also too far from Anatolia.
Okay, thank you. I think we're going to upload this video to YouTube so that people who are interested in this talk would be like have more chance to see the details. And I think it's very easy to find your email. So probably you can talk about the details through email.
Yeah. I will be at SZ too. So
cool. Thank you so much for today's brilliant talk. So, and also have a good summer. Bye. Thank you.